Okay, this is the third video in the Earth unit. First video being Earth's atmosphere, second one being Earth's interior, and this being the third video, which is over continental drift and plate tectonics and how that affects our Earth, so our planet. So anyway, let's talk about a couple of things that should be familiar to you from middle school probably. So I'm trying to whip through this. 1915, a German scientist, Alfred Wegener, started kind of literally putting the pieces of the puzzle together, as you can see in the map up here, and think the continents were possibly connected at some point, and he called this one giant continent Pangaea, which means one land. He also called the ocean Panthalassa, which means one sea. So it's a supercontinent. All the continents as we know them today were basically together 250 million years ago. Kind of a question mark. It'll probably eventually become Pangaea again as continental drift continues to this day. Well, like I said, he literally started putting the pieces of the puzzle together. This is not the only point of evidence that he had. This is where he started, but then he started looking at other pieces of evidence from more of a scientific point of view. This is more of a geographical point of view. So he said that these pieces fit together pretty close, and lots of other pieces fit together as well, but they don't fit perfectly because of the millions of years of erosion along the coastal regions. So a lot of people said, yeah, it's close, but it's not quite perfect, and therefore it probably didn't happen. So it's one of the reasons it was discounted for that one. Another kind of breakthrough from science point of view was that there were fossils of this small creature called a Mesosaurus. And the Mesosaurus is about a meter long, so that's about 3 feet long, so a small kind of caiman, alligator-y kind of thing. There were fossils of the exact same creature found on the southwest coast of Africa and the eastern coast of South America. Wegener pointed to the fact that this small creature could not swim that vast distance, and most people, even at the time, said, "Yeah, you're probably right. That's way too long of a distance for a small creature like that to swim." And plus, you got to think about it. At the time, there were these giant, sharks and Loch Ness monsters and stuff like that floating around. So, this little guy was swimming along the surface, this entire trek. It's a pretty good chance it would have got eaten. So the people that oppose this theory, again, they're always trying to, come up with reasons why it would not work, which, is good science, honestly. But people said, well, there must have been a land bridge there a long time ago, and this little creature must have walked along the land bridge. Now, when this was first being proposed in the early 1900s, ocean mapping was non-existent. So we had no idea if there was a land bridge there or not. So now we know, using radar technology, how that works. But that didn't really develop until the Second World War. Sorry. So another major point of scientific proof was geologically. Geologically, the Appalachian Mountains and the northern part of Britain, right, what is now the Scottish Highlands, and into Ireland, as well as the Caledonian Mountains in Scandinavia. Geologically, all of these match up, which means that they, were the same rocks and probably formed the exact same time and so forth. And when you do Pangaea, this really does make sense. These are probably formed due to continental collision between Africa and North America, right? Appalachians are some of the oldest mountain chains in the world, and we believe at one point they were higher than the Rockies are now, and possibly even higher than the Himalayas. So, but over 250 million years, these things have kind of worn down. So, which the following did not support continental drift theory. Answer is plate tectonics. Plate tectonics is not known about. So continental drift and plate tectonics are different theories. So People said, not sure about this theory. Lots of different reasons why, which I've mentioned as we've been going along, right? The continents don't fit perfectly together. Possibly a land bridge. Wegener was German. This is a major point, and I know that sounds like kind of culturally not correct, but the reality is Germans at this time, this is during World War I, right? Germans were looked upon kind of unfavorably because of this. So he was not given the credit he would not have necessarily, or he would have necessarily have gotten any other time. So the main reason that people kind of laughed at Wegener's theory was, how do you move a continent, right? Locomotion is how something moves. So how do you move something as big as a continent? Well, Wegener said that, and again, this is prior knowledge of things like plate tectonics and what causes tectonic movement and so forth. But Wegener's answer to this was, well, maybe there was like a really strong tidal influence from the moon, and possibly when the moon was formed, and it kind of pulled water away from the planet and then released it as the moon was going around and kind of washed all the continents around. This is as laughable today as it was back then. So this is the main reason his theory was kind of not widely accepted. Now, let's just kind of make it clear that we do recognize that today that his theory is correct, obviously. But the way they move is obviously was not what he thought it was. So this has kind of evolved into the modern science of plate tectonics. So let's talk about what plate tectonics are. Plate tectonics are, sorry, I should have started there. Basically the idea that the upper region of the planet, right, is kind of in these big sheets, and it kind of moves around along these different breaking points, and these breaking points are known as boundaries. So here you see the Pacific plate. This is the largest plate. It is a very large one. And then there's all these little smaller plates, and they're all moving kind of like pieces of ice after it's broken up. So we're going to look at the different types of plate boundaries. You have divergent plate boundaries. So the prefix dive or div means to divide or separate. So these things are moving away from each other. So this is an easy way to remember this. This causes what's called seafloor spreading. Now here you might think, well, there's no seafloor, right? Well, as these things start to move away, it will form what's called a rift valley, which is basically an opening where the land is moving apart from each other. And as they move away from each other, eventually it will connect to a sea, right, a body of water, because it is on planet Earth, and eventually that will fill in with water. So this will form what we now know as an oceanic ridge, which is a continuous chain of volcanoes. So it's basically just volcano, 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 volcano all along the rift here, because magma is leaking up from the mantle, and it's kind of forming right here and continues to separate away. We'll get into that in a minute. On land, it's known as a rift or a rift valley. This is one of the most famous rift valleys. This is the East African Rift Valley. And what you can see is that this, see where I drew it in here, this rift valley is kind of ripping part of Africa off right now. This is what formed the Red Sea, and it kind of rips on down this way. This is why Lake Victoria and Lake Tanganyika, I believe they said, formed, right? Because they formed in parts of the rift, and it's kind of continues to rip down here. You can see how it's making this mountainous looking regions along here. This is why Madagascar broke off. This is why the current countries of Ethiopia and Eritrea are going to break off from Africa at some point. So a little bit of historical knowledge. Biblical archaeologists try to say that the Red Sea connected through the Gulf of Aden. It connected to this ocean at exactly the time that Moses was leading his people out of Africa and into the Arabian Peninsula, or out of Egypt. So as he crossed over, then this opened up down here at the Gulf of Aden, and water rushed in and killed the Egyptians. So just an interesting little tidbit. Other type of plate boundary is what's called convergent plate boundaries. And prefix con means to come together, as in to conference. So easy to remember those things if you can remember those prefixes. 3 different types of convergent. You should know each of these at least somewhat. I'm not expecting this to turn into earth science class, but you have oceanic continental convergence. This is when the ocean crust is moving in this direction, and then the continental crust is moving in this direction. Well, what will happen is the oceanic crust will subduct underneath the continental crust, and subduct literally means to go underneath. And when it subducts underneath like this lithospheric material, right, also known as crustal material, as it sinks down in here and is subducted underneath, will melt down here in the mantle, create excess material, which was not previously in the mantle, and this will cause volcanic mountains to form along the edge here. Places where this happened is along the west coast of the United States, in particular along Alaska, and of course you have Mount St. Helens in Washington, all the way down through the Latin America and into South America as well. So, second type is oceanic convergence. This is when I have an ocean plate coming this way and another ocean plate coming this way. One of them will eventually subduct, right? They're not going to hit each other and just go straight up. One of them will eventually subduct and does the same thing, but because there's not a continent here, these will pop up little islands, and these form what's called island arcs. So Japan is a great example of a oceanic convergent. It's one of the reasons Japan is so volcanic. Mount Fuji, of course. It's also very earthquake prone because these plates are moving all the time, and this earthquakes are caused by plate slippage. Last type is continental convergence. Continental is when two what you would think of as land plates, right, are moving towards each other, and when they hit, neither of them will subduct. So what happens is they both start to upheave. So they come together, and instead of one going down, they both start going upwards. A very famous example of this would be the continent of India crashing into what is now Nepal, forming the Himalayas. So it's a diagram of that. So India is coming in here, right? Nepal, Tibet, over here. You already have oceanic continental convergence, so you already have volcanoes happening here because that's just what would normally happen when oceanic and continental are coming together. But then as India slowly but surely started colliding in here, right, upheaval started, and it formed what we know of now as the Himalayas. So you can see in this little timeline, 71 million years ago, 55 million years ago, 38 million years ago, 10 million years ago. So this is rapid movement. So this is a little faster than what we would, even calculate continents to be moving today. So India is still driving into Tibet, Nepal area, and as a result of that, the Himalayas get about an inch taller every year. Sounds like a small amount, but geologically, that can definitely add some. Next type is transform fault. Transform fault boundaries occur only at divergent boundaries, but what happens is a slip occurs. So you can see how this one was going this way, this one was going this way, and then this one was going this way, and this one was going this way. Well, what happened was a slip. These used to be all lined up. Where this yellow is and this yellow is used to all be together, and it was forming an ocean ridge. But what happened is something slipped in here, and now you have these two regions that are opposing each other. This one's going this way, and this one's going this way, and as a result of that, lots of friction occur between these two things. And it'll build up this friction, and it will cause massive slips of the soil or the earth, and these massive slips will cause what we feel is seismic activity and or earthquakes. So California is one of the most well-known places in the world that has transform fault earthquakes. The San Andreas Fault, of course, runs right outside Los Angeles. Runs kind of straight down in here through the Gulf of California. Now, a lot of the slipping that occurs occurs in several places here too, but also along this Juan de Fuca plate. So as the Juan de Fuca plate pushes against the Pacific plate, the Juan de Fuca plate is pushing this way, and then the Pacific plate is pushing this way, and this causes lots of seismic activity from that. Is California going to eventually fall off into the water? Who knows? So the type that's not is a Pangea fault. No such thing. Alright, so how do we know plate tectonics is going on? This is always like one of those things that, as you know, as a teacher, it's kind of hard to explain how we don't really see this, right? We don't see this lithosphere subducting underneath here and then melting and popping up these things. We don't take a big slice of the planet like we do a piece of cake. We don't see this. We have to look for evidences of this. So we're going to see what those evidences are right now. One of the main evidences we have is what's called paleomagnetism. And it's a record of magnetism over geologic time, because, as you may or may not know, the magnetic poles of the planet switch from north to south on a fairly regular basis, and again, geologically, about every 150,000 years or so. So when we see paleomagnetism easily kind of identified through a volcano, because as a volcano spews out, right, magma, the rock in it, which is, if it's igneous, will solidify. Igneous means from volcano, of course. The iron in this rock will magnetically align with the magnetic pole at that time. So if you look at the different layers that it's pointing to here, you have 1.2 million years ago here. Then, what is it, 0.4 million years later, another explosion occurred and another layer of magma kind of laid down. And as it cooled, it was going the opposite direction as far as magnetically. And again, you have another reversal in the next, 0.4 million years. So that's how, now this is not related to plate tectonics, but this is how this was leading to a point of plate tectonics proof. So just bear with me for a second. This is an example of some of the different magnetism flips. These are just different periods that they've named based on pole reversals. You don't need to know that. Now, where we use magnetic reversals to explain plate tectonics is that seafloor spreading. So this is kind of a difficult diagram, so really pay attention. When magma kind of leaks through this oceanic ridge right here in the middle, remember it's like a continuous chain of volcanoes, as it leaks through and dumps this magma on either side of this, right? These will be both dated the same. So notice I wrote a 1 and a 1 here. These will be dated the same time because they are laid down the same time, and they will be magnetically aligned to the same pole. So the next major, time that it lays down magma is 0.4 million years later, right? Well, when it lays down new magma, it'll have a different magnetic polarity, which means that the poles flipped. Now, what we notice is bizarre is that this rock and this rock are the same age and have the same magnetism. That's puzzling, because how are these the same, but then this is newer? Well, then when you look at it even another layer, right, you see 3, this is the newest magma, has been deposited, and it's magnetically aligned in the same direction that 1 is aligned. Well, if 3 and 3 are the newest stuff, and we can test this geologically, right, we know this is the newest stuff, well, then we start looking at 2 and 2 were laid down at the same time, and they have a different polarity. Well, then we look at 1 and 1, and they were laid down at the same time with similar polarity, or the exact polarity, how could 1 and 1 get here when it used to be here? And the answer is that it's slowly moving this direction, right? Notice this, it's a divergent boundary, so it's slowly pulling this way. So paleomagnetism helps us to easily identify regions where this occurs. Another interesting way to prove plate tectonics is by earthquake foci. Earthquake foci are basically the place where the earthquake starts, and we can track that. And we plot this data. So for instance, this is in an oceanic ridge area where two continental crusts are coming together. And we start plotting these different earthquakes that occur around this, right? Because they're happening pretty regularly, especially around a place like Japan. Japan has lots of earthquakes for this exact reason. Probably more earthquake prone than California. So here you see lots of what's called shallow, if you look down here at the key. Lots of shallow type earthquakes. Then down here you have what's called a medium or intermediate type of earthquakes. And then you have some down here which are called deep earthquakes. Now if you look over here on the map, here's Japan. And we start tracking these, right? These shallow, shallow, shallow. Then we start seeing some of these intermediates. Intermediate, intermediate, intermediate. And then we start seeing the deep, 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 deep. Right? So it goes shallow, intermediate, deep. If you look at it on a topographic map. So something's going on, right? Why is there friction down here? Why is there friction here? And they all line up together, right? Shallow, intermediate, deep. One of the reasons is we believe that this crust is subducting underneath. Again, remember, we're not taking a slice of the planet and looking at this and pointing to the lithosphere subducting underneath it. We're using earthquake foci data to say, okay, there are shallow ones here, okay, there are intermediate ones here, and then there are deep ones down here. So we're kind of tracing the way the subduction zone works based off of earthquake foci. Another visual clue is this right here, which is called the trench. And the trench always forms where two crusts are actually coming together. It's where the subduction zone starts. So the trench is actually a visible cue. You can see the Japan trench here, right? This is showing where they first hit. So another major way we can prove plate tectonics is through hotspot plate movement. Now, hotspot volcanoes occur over what's called a weaker area of the lithosphere where magma is just allowed to kind of seep through. Now, this is how the Hawaiian island chains formed. Now, the Hawaiian Islands, some other very famous islands you see on this little map here, the Midway Islands and the Emperor Seamount chain, these all formed over what's called hotspots. Now, hotspots are important, so we'll get back to that when we get to Venus, because Venus has lots of hotspots. This is how their volcanoes form. Now, what happens is a hotspot is a weak area, like I was saying. Magma kind of leaks through. Well, what happens is the plate keeps moving, right? So if you notice this arrow here, the plate keeps moving, but the hotspot stays the same because it's not attached to the plate. The hotspot itself was technically down here in the mantle material, but the plate is what keeps moving. Well, as the plate moves, it'll keep depositing this magma, just kind of leaking through, and it makes new islands. So if you look at the dates of these, I'm not sure if I'm pronouncing these right, so Kauai, I'm not sure how that's pronounced. Anyway, this island was formed 3.8 to 5.6 million years ago, right? That's a fairly young, geologically young island. Then Oahu is 2.2 to 3.3 million years ago. Molokai is 1.3 to 1.8. Maui's less than a million years ago. Geologically, we can test this, right? In the present day Big Island of Hawaii is less than a million years old, right? 0.7 million years old. Well, that's because it's currently over the big hotspot. Well, the plate keeps moving, so we're going to have additional islands keep kind of popping up here in a regular pattern, right? And there's already a new island starting to form off of Hawaii. It's still underwater. hasn't broke through the surface yet. So I kind of did a great little visual down here. At least I think it's great. Let's see if I can get this to working. It's kind of not very cooperative sometimes. So okay. So if you notice down here in the very bottom where it says HS, that is the hot spot. Now imagine what I'm moving here is the crust. So boom, new volcano. That's an island. Psh, 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 psh. That's my crust movement sound. It moves, and boom, the hot spot's going to keep leaking the magma. It makes a new volcano, and every new volcano, in this case, is a new island. Boom. Crust keeps moving, hot spot stays in the same place, new island. Boom, new island. Boom, new island. So, I think this is a fairly horrible visual, as I'm sure you're quite aware, but I think you get the idea. So, crust moves, hot spot stays there, it keeps making new islands, depositing them. Alright, so last thing about plate tectonics is what causes this to move? Why are these things moving? And are they just moving arbitrarily or just kind of floating around like ice on water or what? And the answer is no. We do not believe that they're moving arbitrarily. We believe that convection within the mantle pulls these plates apart. So the core is hot, right? If you didn't know, I think I've mentioned it in an earlier video, it's hotter than the surface of the sun. So the magma around the core is going to be hotter than the magma up here, right? Because it's fluid-like. So it will therefore start to flow. Because convection, of course, causes things that are hot to rise up, and then as it cools off, it will kind of sink back down. So this has multiple convection units, or convection cells. So you have the lower mantle, then the upper mantle will start to convect off of this lower mantle stuff, and this is a little, probably thicker material. This is like probably a little bit more liquidy. So this pulling apart from each other is what causes the plates to move, especially at seafloors. Seafloor spreading is really what causes the entire plate system to move. These divergent boundaries where you have, trying to see a good example here, where you see, trying to look here, here's a good one. What you see is as this heat transfers to this, you have these smaller convection cells. This convection cell is pulling this way, right? And it's going to keep kind of convecting in this general pattern. Well, then this convection cell right here is pulling in this direction. So as it pulls this direction and then this one pulls this direction, it's going to cause this little rip here, which is the oceanic ridge. This will cause the convection of the mantle underneath will cause this plate to move this way, and will cause this plate to move this way, because it's really all the plates are just floating on top of this mantle material. So, alright, that's my quick overview of plate tectonics and continental drift. If you have any additional questions, please don't hesitate to ask me. I'm happy to go over this stuff in class as well. So, see you then.